Perfect. Many of you, I know, are already familiar with Women in AI, but for those who are not, Women in AI is a nonprofit, volunteer-led organization working to promote ethical, inclusive AI that benefits the global society. The organization is designed to empower women and minorities to become AI and data experts, innovators, and leaders. Women in AI has 8,000 plus members and growing, and has a presence in 140 countries. If you would like to join Women in AI globally or in the US, you can see the information listed at the bottom of this slide, or simply go to get started, go to womeninai.co, and registration is free. There's a lot of great programming. Go to the next slide here. As I mentioned before, this event is part of the Women in AI Engage USA series. These are monthly events that are designed to engage women and girls of all backgrounds in the AI community and to provide knowledge and resources and a sense of community. So we're really excited to present this second go around for the Engage series. I do want to take a quick moment to give a shout out to our organizing team. Events like this require significant coordination and effort, and I just want to say a big thank you to all of our volunteers. The team has grown, so we no longer fit on one slide, so I'm going to go to the second slide here. And with this growth, there's new possibilities opening up, so please watch out for more great events and content coming soon. So thank you to everyone that's put effort into making this event possible. All right, so now on to tonight's event. I am very excited to introduce our speaker tonight, Dr. Jennifer Rochlis, and please correct me if I have not said your last name correctly.
It's Rochlis, like the CH is like, okay, no worries.
Rochlis, okay. Yeah. Thank you for saying that. Tonight, she'll be discussing advanced AI systems and the importance of designing human-centered autonomous products. Let me move to the next slide. Introduction. Dr. Rochlis is currently the Vice President of Products and Solution Architecture at Teledyne FLIR Defense Systems, in which she's responsible for the unmanned aerial, unmanned ground, integrated solution and detection portfolio family of products and solutions. Dr. Rochlis holds a PhD in aerospace, aeronautical, and astronautical space engineering from MIT, and has an almost 20-year career at NASA, where she received a Director's Innovation Award, a Director's Commendation Award, and a NASA Agency Honor Award for her efforts in human systems integration, research, and development. Dr. Rochlis, we are honored to have you here tonight.
Thank you so much for having me.
Yeah. Let's go ahead and launch right into the interview, because I have a feeling that there are going to be lots of questions at the end, and we want to make sure we have time for that.
Great. And do you want to like stop share so we can make ourselves bigger? I don't know if you want to.
Yes,
you might absolutely. Not want to see my bio for an
hour. Very true. One other quick, if you have questions, we're going to save all the questions for the end. Please drop them into the chat and we'll get them organized to ask at the end. All right. Perfect. So let's just kind of start at the beginning. Dr. Rochlis, you have such an impressive expertise in AI. Could you kind of start off by telling us about some of the AI projects that you've been involved in at Teledyne and NASA?
Yeah, absolutely. So I'll start with NASA. About 20 years ago, I went there. I was still finishing up my PhD, and I was honored to go work on Robonaut. And I'm going to show you a picture of it while I talk about it, because it's very much in the frame of why we started thinking about partnering. So Robonaut was designed to be a humanoid in form so that it could really partner with an astronaut and help him or her accomplish their mission tasks. And the way that we started doing this was with teleoperation. So we would manually move the joints and the head and the neck. It definitely has a personality. People anthropomorphize it for sure. We like to give it names. And the crew members who work with it really start to feel like it's part of the team. But when I was there, this is the second generation of it, by the way. It was an arm and a hand and a head, and we really didn't know what we were doing with humanoids, and we didn't know how to operate them. So it was all brand new and really a great time to be there. But ultimately, we knew that we had to build more smarts into the system and make it more user-friendly. So we created a host of autonomy and AI initiatives to sort of create what we called it a sensory egosphere is what we called it at the time. So a way that the robot, kind of like a human, would know what was in the environment around them, be able to autonomously view objects in the scene, plan a path to it, and then work with the astronauts. So I'll show you another picture as well of what that looks like when we do it in the lab. So this is what we did. We built, and you can see this is like the earlier versions are a little larger, not quite as sleek, carbon fibers, things floating around still. This is astronaut Nancy Curry. She's one of my heroes and mentors. And so she's working with 2 different Robonaut units. And what she'll do is say something like, hand me the wrench. And the robot would go and survey the toolbox and look around its site to see where it was. And it would remember where it last saw it so that it would start there and then plan a path to move to it, pick it up with a grasp that it could determine based on all the tactile sensors in the glove, and then reach out and hold it until she asked it to release. Because remember, in zero gravity, you don't want to ever let go of anything. You won't see it again. So important that we start to practice these things in the lab and the coordination and the communication. So as we had more and more advanced autonomy on these systems, we really could explore some of the capabilities. And then interestingly, we took all of that knowledge that we used with that robot and high-level tasking that we were able to do, which basically offloaded the operator. So rather than having to drive it manually, right, you would say, find me the wrench. And so we said, how can we take that and move it onto different platforms? So the next thing we did was we started to look again at rovers for the moon and Mars. And this is like a 3rd or 4th generation version. It's a pressurized rover as opposed to an unpressurized, which is where we started, very grassroots. We took the old lunar rover trainer, bolted things on and off just to see what would work. And it became a pressurized system they could live in like a camper for a few days out on the surface. In the back, their suits would hang and they would slide in and out of the vehicle through there. But what we wanted to do was take all of those smarts in that sensory system, put it on the robot here so that it could autonomously drive to waypoints. You could set courses based on items of interest or places of interest. It could remember its path planning. We would look at state information such as the fuel levels, and I say fuel levels, but fuel levels, and plan routes to say, well, I can make it to this site and this site, but then I'd have to go back and recharge. So some smarts in terms of state information. We also had something that the astronauts really loved, which was a following command. So when they got out of the rover and they dismounted, they would start walking, doing their science tasks, and they could ask the robot to basically come pick them up. So this is pre-Tesla. So I should say this was back in the day, this was really exciting that we could have the car follow them and keep a safe distance so that they wouldn't have to spend the breathing resources to get back and the muscular resources to get back to the vehicle in the spacesuit, because time is everything in the spacesuit. Every moment counts. So what we were doing was building advanced systems to really augment and assist the human with what our tasks were for the astronauts at the time. So that was sort of the NASA piece of it. But then there were other parts that we did at NASA too that were really interesting, where we're looking at defining all the requirements, not just for the rovers, but for the systems on board, say a space station or a habitat on the moon or Mars, something like an environmental monitoring system. So making sure that smoke detectors, carbon dioxide monitors, trace gas contaminants, things that you wouldn't be wanting in the atmosphere, leaks and things like that. So as many systems on the vehicle that can run autonomously is important. And then learning about where the AI comes in, not just autonomy, but learning really what to expect in terms of level so that it can really notify you when there's something off nominal as opposed to just a small variation. So it was learning over time is how we would move out with that. And lastly, I would say that the doctor in a box kind of concept was always really helpful. So we can't fly every expert that we have experiments for. So how do you replicate someone's thinking and problem solving on a computer chip that can help you if something goes wrong while you're doing an experiment? So that was another area we tried to use AI, as well as fault detection, isolation, and recovery. We called it FLIR. Again, a way for the system to try to isolate a problem and offer you examples of what you could do to recover from that problem based on integrating a large amount of system information that the human wouldn't be able to do in time, especially if there was a critical event. So the last one I'll mention, after NASA and going to FLIR, they had just acquired a series of systems and companies that did ground and air robotics, both at the nanoscale and the Group 1 class, if you're familiar with those designations. But really, we're looking at how do we keep as much distance as possible between good people and bad things. So it's how do we get the robots out into the field, into the air, and keep our troops back and safer. So those systems, again, are really exposed to environmental hazards, just like you would imagine in space. Extreme temperatures, extreme lighting conditions, extreme heat, dust, wind, rain. We have soldiers who use our equipment like they're Nerf toys. So you have to have them very, very robust. And really the goal is to have the person operating it have to do as little as possible, just the right amount of workload to keep them so that they maintain their situation awareness, but not too much that they feel like they are compromising their awareness of their environment, especially in a critical situation, because they have to operate a robot. So things also like communications jamming and loss of signal, all of those things, we have to have the robots operate in all of those situations as well. So how do you keep something running, not colliding with objects, mapping objects, tracking objects, and then the learning that's involved in there is about, hey, I see an object of interest. Can you tell me what that is? Is it a truck? Is it a military vehicle? Is it a civilian person? Is that a deer for an automated car? So all sorts of tracking and classification is where we are building most of the AI into those systems. So let me pause there because that was a lot.
No, that was wonderful. Thank you. Those are fascinating projects. Yeah, one of the things that I hear you saying is just over and over is the intersection of humans with AI and, different technical levels of users. Could you explain what human-centered AI is and kind of why human-centered AI product design is so important?
Yes, absolutely. So I think there's a misconception, or there used to be a misconception at least, that what AI was going to do was sort of replace the human. And there's still quite a bit of fear, I would say, around that concept of, job loss and such, which in some cases is true as you think about manufacturing plants for automobiles. We've seen how the level of human touch on those assembly lines has gone down over the years. So there's certainly a point to that. It's really about dull, dirty, and dangerous. That's sort of the triple D word that everybody uses as this moniker to say, wherever is a dull task or a dirty task or a dangerous task, let's put some sort of autonomy or AI in the picture to kind of allow the humans to remain safe. It's also too about when you're looking at AI systems, typically you're trying to either augment or bolster human cognition. And in some cases replace, which I think we've seen in the last few years, some of the really amazing work in text and speech recognition and speech generation has come incredibly far with the amount that they've been able to learn and teach, learn from and teach the AI algorithms about our human speech patterns. So because the entire point is to either work with, near, or around a human, we have to take into consideration all of the phases of that design and development where a human is going to interact with that system. Because really the system, we have to really change the definition. People like to think of a system as a widget or a mechanical object or a piece of software, and then the human is the operator. But really, my Kool-Aid that I've been spreading for years is that we have to redefine the system as the human plus the software plus the hardware. So you cannot separate the human out of the system when you're defining it. And that's the first step to really making sure that you're designing these systems for their intended use and for operator aid. So one of the things that we looked at a lot at NASA was, I think we're going to talk about partnerships in a minute. So we'll talk about trust in a second, but certainly looking at what kind of capabilities and outcomes you're trying to drive is important. You can certainly do autonomy for autonomy's sake. And there are a lot of things that we could automate and could put learning around, but should we? And is that always the best idea? And a lot of times we also think that taking humans out of the system reduces errors, but really, in fact, it just replaces the type of error. and changes the nature of the error. And so we have to have a break-in period with some of these systems to make sure we understand how the humans are operating with these new algorithms. And we've seen some unfortunate incidences, such as 737 MAX, where that wasn't well executed or trained. And so it can be very catastrophic if we're putting in advanced autonomy and AI in situations where we haven't really thought through the human considerations.
Yeah. Again, fascinating, and so much goes into that. When you are thinking about human partnerships, how do you approach that with autonomous systems?
So the one I was going to mention earlier about trust, one of the ways that we started thinking about this for Robonaut, and it kind of trickled into everything I've designed in the future, is really modeling the work on human-human teams. What makes human-human teams tick, so that we can understand how robotics and AI and autonomy would fit into that paradigm of trying to partner with a human in that case, to either do a task or to provide information that the human isn't capable of generating on their own. So done a lot of work on trust in human teams, and I'll just share with you all some of the things that make human teams successful, and how we kind of translated that into what it would mean for AI systems. So typically humans who are teaming well have a shared common goal and shared mental model. And those two things are different, but very important. So what is the outcome we're all trying to drive? Where are we trying to get to? What does success mean? And do we all agree on the foundations of the environment that we're in and the rules that we all have to follow? So if we're all trying to play the same game and we all know the game is to get the most points, do we all understand the same rules? And if we don't have the same mental model of how the game is played, it's going to be very difficult to build trust in that team who's all trying to work together to be the team that scores the most points. Another interesting thing about humans and teams is typically there's an expectation at some point that you will subjugate your individual needs for the group needs if push comes to shove, which is interesting to see how we would even approach that concept when we talk about autonomy and AI. And then also that there's a view that interdependence in general is a positive thing. So it's not a bad thing to have to rely on someone else to do a task. Typically for our astronaut crews, all the help is greatly appreciated. And so there's an opening thought that this is a better, outcome with this robotic assistant or with this AI assistant in the mix than without. But in commercial industries, that isn't always the case. So there's something to think about as we look at what areas we want to put these systems into. And then everybody has to know their own role. Like, what's your lane? What are you supposed to be bringing to this team? And how do you fulfill that? And are you doing that reliably? And so those are just some ideas about where the human trust on teams comes from that we then translate. So things that have to happen before you can start trusting these AI systems is on the human side, we look at personality traits, we look at prior experience. We'll say, I understand how you operate, I understand how you tick, I know how to talk to you, and I understand what you've learned and what you're bringing to the table. So I think I have a sense of who you are. If that's a robot you're talking about, it's really about consistency and performance. So it's not that the robot can never break, because we expect every robot at some point, or every AI system to fail at some point, everything to crash at some point, and humans do that too, by the way. So it's not that we don't ever expect that, but it has to be consistent in the way that's happening. So is the system, is the algorithm, is the robot failing in the same way every time, or is it seeming erratic? In that case, trust is very hard to recover. And then there's environment related. So if everyone understands in the team what that shared situation awareness is and how complicated the task is, that tends to be something you have to have in place before you can start designing these systems and operating these systems together. So there's really a calibration phase, and I alluded to a little bit earlier about how critical it is to deploy these systems and iterate and iterate and iterate, because we have to wring out all the bugs and then wring out all the errors that we're going to be seeing that we didn't plan for or we couldn't have predicted in the design phase. So you calibrate over time, and you have a learning curve for humans, and you have a learning curve for AI systems as well. Because as we've seen on the battlefield, if the troops don't trust it, they won't use it. They just shut it off. So even though it's meant to aid them, it's actually more harm than good if it's something where they get a lot of false alarms or missed events, and they can't wind up trusting it from one day to the next. They just don't use it. So it's not a really well-designed capability in that case. So interestingly, as trust builds, you need less and less validation. So in the beginning, it's like almost constant. You need to constantly be giving continuous feedback about how's the AI doing? Is it giving us the result we expect? Do we trust the outcome? Do we like the recommendations the system is giving us? Do we think it learned appropriately? Did it interpret that, visual correctly? Did it label it correctly? Did it track it well? And once you start to build that trust, then you can sort of relax that continuous nature of the feedback. But again, it's not that we don't expect it to ever fail, but make sure and you're expecting how it might. So those are sort of some nuggets about how we even approach, at least how I've learned in my past to approach designing these systems. And I think that another piece that we have to really touch on is cultural norms and differences in like even just across countries. So for example, at FLIR, we have a department that our defense department is 4 different countries of folks that are all designing an algorithm for the same purpose. And even just how you build learning systems and what cultural norms do to influence algorithms. We can talk about what biases are built into them. Not that bias is a negative word, it's just a slant of one way or another, but we all have to look at very clearly sort of what are the expectations that this culture might give as a parameter on how we design the system that another country may not recognize the same way. We learned this also very well on the space station when we had multiple countries all the time, and the way in which the different folks from the different countries used the equipment often generated a lot of good feedback on how we could design our systems better. So it's not that there's one model of a human. Humans are very messy and they're not always predictable, but that's why we'll always have a job. And that's why I love doing this work. So.
Yeah, wonderful. Yeah, one of the things, as you're talking about kind of differences in culture, you're talking about how these systems need to be very robust and everyone has to understand the rules of the environment. How do you adapt these designs to change when your environment changes?
Yeah, so there's like a hardening of the system that you have to look at when you're setting up your requirements at the beginning. That's where that all comes in. So when you start out to design a system, you're going to have a concept of operation. You're going to say, how do we envision using this system? What is the role of everyone in this? What are all the agents' roles going to be? And what are we trying to drive the outcome around? So what is mission success? I mentioned that earlier. And when you do that, you start to say, okay, so if this is what success looks like, and this is what the outcome we're trying to drive, now let's back out of that. What tasks have to be done in order to accomplish that set of mission goals or tasks? So you do this task analysis, which is the next layer of that. And when you do that task analysis, you're looking for environmental conditions, you're looking for, let's say you're looking for temperature ranges it has to operate in, or weather conditions it has to operate in, lighting conditions, as I mentioned, vibrational conditions, gravity conditions in many cases for NASA. And you would spec out all of the potential arenas where that system could be used or deployed. And then you have to start making trade-offs, because typically what you'll find is it's either too expensive, or you don't have the mass, or you don't have the volume, or you don't have the dollars to actually build a system that could do everything for every environment. So you start to have to narrow down the criterion and say, these are the things I can meet on the requirement side, and these are the things I can't meet, or I can, but it's going to be at the expense of something else. So if you're using a system in totally different environments, you have to kind of do that analysis to say, is this something that's really worth retooling to work in a different environment? Or is this something I need to design from scratch, the custom fit for that environment? And that's a trade-off we make all the time. I'm glad you asked about it, because it's a nuance that's really important. Chances are if you build something to do a little bit of everything, it won't do anything terribly well. So we look to see, where is it really critical that it operates and when, and then we probably should design around that. And the other things would be a nice to have, or they would be in the world of requirements, they'd be shoulds as opposed to shalls, meaning they're not, mandated you have to have it, but you probably should if you could. And by the way, sometimes those are differentiators that the operators really care about. So when someone's designing a system for an outcome and you start to deploy it and you start to see what's important, I mean, if you think about the iPhone when it came out, they're like the luckiest designers in the world because they get millions and millions and millions of user inputs in an instant, because people will tell everybody what they think about the iPhone interface when it first came out, which gave the designers instant feedback as to how to do it better. In our cases, we don't always get the feedback right away or as quickly as we'd like. So a lot of times the designers have to make some smart, educated guesses about what the use case is going to be, especially for a new system that's never been deployed. So it's really hard to guess ahead of time, all of those things.
Wow. This is fascinating. And these products are fascinating. I am thoroughly enjoying this.
I can't even see you, so I'm just looking at myself, but I'm having a good time.
So I know that at the very beginning, you gave us some examples of the products that that you worked on. Would you be able to kind of walk us through maybe one or two examples of some of the products that you've helped develop kind of from start to finish? Because I think our audience would be interested in how a system is built from scratch, what AI is involved, and some of the tactical decisions that you would need to make.
Yes. So I'm actually going to start with one that is something that's being built in another part of our business right now. It's also out on the roads already, but I think everybody can relate to it, which is sort of automated driving, because I think it's something everyone has an instant understanding of sort of the complexity about. And there's also some really interesting recent research that came out in the last week that I'll share with you as well. So again, when you're looking at, let's say, how about we see what we could do with putting AI in a car? What would it mean to relieve the operator of having to actually drive it? And what are the implications of that? So first, you're going to look at, what is the concept of operations of a car? What is the goal? Obviously it's getting from point A to point B safely without hitting anything. And there are all sorts of rules of the road that you have to design into that system. You have to know about speed limits and lanes and all of the driving rules that teenagers love to learn. So first you list out, and you're basically doing this ConOp evaluation about what the goals are. What are your high level goals for this vehicle? And then underneath that, you would say, okay, let's break that down into what are all the tasks involved in driving. And I won't bore you with all of them, but if you just think about it from beginning to end, there are some like, walking up to the car and seeing if it's locked or unlocked. And then how do you open the door? And then how do you do your seatbelt? And then how do you adjust the mirrors? And then how do you turn the car on? And et cetera, et cetera. Checking the fuel gauges, all this sorts of things. You guys might, I don't know how old anybody is on the call, but you may remember back in the day, it was really popular to have those automated seatbelts that would close for you because they were like, it's just too much work. And we don't want people to forget it because there's new laws about seatbelts and most people hated them and took them off. So, but things like that, where you would say, you go through and you would list literally task by task. It's really, really an exhaustive look at every single thing that you would do to drive a car. And then you would want to say, okay, what could be done either automated or with some AI in there, artificial intelligence, and which ones should be done with AI? Because you could automate a ton of things, seatbelt as an example. At some point they decided that was just not worth it. So you have to sort of do a little trial and error to see all the options that you could do, what is really prudent to do, and what should be done. That is really the first place where it's a little bit of guesswork and you're going to do your best, but chances are you're going to come back to that step many, many times. You'll automate something or you'll put some intelligence into something, and somewhere in the design process, it won't go very well. And you'll realize maybe we shouldn't have done it that way, or maybe we shouldn't have done it at all. And let's go back and take another look at it. But in any case, you've made a selection of things that you could automate. And then you have to ask yourself sort of what level of human oversight and intervention are you going to allow and require? So, okay, let's say we automate something. Let's say we automate the steering in a lane. So stay in your lane, and you're driving in an automated car, and it's supposed to avoid collisions by using its cameras on board. And the way that it's doing that is it is scanning the environment. It is pulling in all the visual data, and it's searching through databases and algorithms to determine that's a car, that's a person, that's a child, that's a stroller, that's a bicycle. And you're hoping it gets it right, because the way that the car would react, if it needed to react to, say, a car coming at it versus a child coming at it might be very different. So you would go through and say, when does the human need to be made aware of what the autonomy or AI is doing? And when does the human have to actually jump in and do something? Or when can they? When do we even let them do something different? So I'll do two examples in parallel. The other example of this is on the space shuttle. Because most of the astronauts historically have been pilots and test pilots, there has always been a very strong desire for the astronaut crew to want to fly everything we build themselves. In the case of the space shuttle, when it initially takes off from the launch pad, the speed with which it's going prevents humans from being able to control it, because there's no way that our body and our brain and our reflex loops are fast enough to actually affect the control surfaces to be able to steer the shuttle in any meaningful way, without probably making it worse. So we actually lock them out of flying it in the first phase of flight. And when it gets to a certain point where it has slowed down a bit and there's something that they could possibly do to impact the vehicle, then we open up the trade space again. And to give you an example of the millions, we ran some AI codes to say, of all the millions of possibilities of ways that the human could push on the stick to maneuver the space shuttle after it takes off, how many ways could the human actually control it? And of the millions, there were 11 ways, 11 situations where the crew could actually jump on the stick and do something meaningful and try to land it or steer it away from something. So that's a very small number, right? So this gets back to sure, we could do it, but should we do it? And so we did a whole bunch of criterion around those 11 scenarios where we would allow the astronauts to jump on and actually try to affect something in the outcome. So anyway, going back between the car and their analogy, the next thing you would probably do is say, what are the safety implications then of the choices that I've just made? So if I choose to not let a human intervene, that has a safety implication. And if I do have the human intervene, that has a safety implication too. I'll give you an example. So let's say a bicycle or a child walks in front of a car. If the automated system is faster at responding to the brakes than a human would be in that situation, it's probably better to have the automation do it. But if the human needs to make a judgment call about whether or not you should steer around it, or whether or not it's something where it was actually a false alarm, it wasn't a child, it was a balloon that rode by, it could actually do more harm than good trying to slam on the brakes. You could get rear-ended by somebody else. So just as an example of why you want to run all these kind of to ground, and it's not as straightforward, but this is where all the human systems integration part really comes into it. Then there are things like, what are the training implications for the system that you're developing? How do you teach a human how to use your system? And I will tell you, I have a Tesla and nobody taught me how to use it. So it's trial and error, and I design these things for a living, and I can tell you all the ways I love it and all the ways I hate it. But nobody ever sat with me and told me how to do it. Which is, I think, a little bit something that we should look at as a policy when we're starting to put these kinds of cars on the road. We have, students, when they're learning how to drive in the first place, they have to prove everything that they understand about the car. But we don't do any tests with automation today, which I think is almost a little irresponsible, but it's important. And then there are also some negative training implications, and I'll give you another personal example. So my son, who turned 16 today, he's getting his driver's license, and I really didn't want him to drive my Tesla because it does enough things for you that he won't learn the hard way. He won't learn the manual way. He's not understanding that, hey, the car is going to do this, but really you're going to have to do this yourself if you drive someone else's car. So that's sort of negative training, because it makes it so that you don't have to keep practicing that skill, and you get skill loss. So you just get more. It's called bench sitting. We used to call that bench sitting. If you're a sports fan, if you're sitting on the sidelines for most of the games, and then the coach is like, hey, get in there, and you're like, oh my gosh, I'm so out of practice, I don't even know what's going on, I haven't been paying attention, and your reaction time is much slower. So that can be a problem too. So last couple of things I'll mention is well, then you have to choose the algorithms that you're going to use. So what am I going to do my learning around? What am I going to say that I want it to project out into the future, which is the artificial intelligence piece? What am I making assumptions about going forward? What states am I going to predict are going to happen, so that I can decide if these are things I want to alert or do anything to the car about? Do I want to move the car? in response to this signal I'm seeing, or do I think it's not really that important? So those are all assumptions that you're making when you build those algorithms. And we mentioned bias before. So this is where I'll mention there was an article that came out, I could send it to those who are interested, that just did an anecdotal study about the fact that there's even gender bias in responses to automated cars, and that women were shown to significantly more often than men were able to intervene and react to a failure in the automated system than a man would. And I said to them, I was looking at the article and I was like, I wonder if they tied this to the brain and cognitive science part, where the task switching, for females is wired differently than for men, which is more serial processing in nature of the brain design. So if they don't think about that when they're building it, they might not notice that there's a gender difference in the way that men and women approach the car driving experience. So just all sorts of layers of that, which are, you could go into for a long time. And then the last piece I'll mention is, how are you going to train the system with data? So I mentioned the car example. We need to train it what a bike looks like, and what a kid looks like, and what a balloon looks like, and what another car looks like. But a bicycle coming at you looks different than one coming from the side, looks different at night, looks different during the day, looks different when it's 3/4, looks different if it's got reflective tape. So if you can imagine, to teach a system what a bike looks like takes a long time. So if you guys ever have a website where it says I'm not a robot, and you guys click on all the times you see the bus, you're training all the AI systems. I don't know if you know that, but you're training all the AI systems to get variations on what all these items look like, so it can teach automated systems how to interpret the data. So you guys are all experimenters.
Wow. Okay, I just learned a lot. That was fascinating. I have a few comments. So one, I also don't know how old everyone else is here, but I am certainly old enough to remember the automatic seat belts. So if that, I do remember that, and kind of getting hit in the face once or twice, not paying attention there. And then I thought the portion about the not having the training, and sort of, if these cars come on the road, like having a re-education for all drivers, that's really an interesting point.
Yeah.
And I also didn't know that when I select the things, I'm doing a labeling task for different companies. That's fascinating. So thank you for all of that information.
Sure.
I think that your example is a perfect one to kind of launch into the next question. And I think you answered and covered a little of this, but kind of veering away from the technical side. But I do feel like advanced AI and autonomy is so heavily discussed right now. Could you give us kind of an overview of some of the topics and concerns being discussed?
So we touched on it a little bit earlier when I mentioned about kind of AI and robotics and autonomy taking over jobs. But rather than that be the conversation, I would rather the conversation be around the nature of work, because the nature of work is changing in general. And I think in the last 20, 30 years even, and you could see even with the pandemic, with so many things moving online, the understanding about what can be done via computer versus in-person interaction alone, and the expectations that we put on the systems are very different. So I actually would kind of go back to basics and say, what do we think work is going to look like in the next 20, 30 years? Because I think we were going down this path where AI was just going to take over thinking hard, right? And it was going to be taking over big data, and it was going to be taking over crunching numbers. And you've seen if any of you are on social media, you've seen what algorithms do, right? From guessing your ads and, showing you videos that you want to see, and telling you when you should be seeing your friends' feeds pop up because of how often you've interacted with them or liked their post. So all of these things are being done, and they're actually driving behavior, as opposed to looking at the behavior of work and the behavior of technology and humans' interaction with it, and letting that drive the conversation about what we should automate. We're actually letting some of the advanced automation that's coming out drive the nature of work. That makes sense. So I'd love to have that conversation more. I also think I would love some conversation around sort of what level of comfort and error do we require of our systems. So let's say in my day job right now, it's a really critical issue. If I send a robot out into the field that a soldier is expecting to do something to help save their life or impact a mission in a life critical situation, or in a space station when a tiny little hole puncture can lead to some very bad outcomes. When you're designing any system that is life critical, how good is good enough? How many failures is too many? And if I could never make it perfect, then when do I say it's okay to let it out? And then where's the liability on either side to say, in the government side, a lot of times they will say, we understand, because, the DoD understands, Department of Defense, that they're buying a lot of systems that haven't been tested, or they're buying new technology, and there's sort of an acceptance of some risk in some cases. Certainly astronauts, when they come to work for NASA, they know that everything they're going to do for their day job is going to be life critical. And that's sort of an implication. So, but not everybody who gets in a car that has some part of it automated is agreed to that. So I think that's a really interesting question, is sort of what level of comfort do we have with the level of errors that we're putting into systems, or that we're introducing in general. And then assuming the worst case happened, could we live at that? So I think people are very glib about saying, oh, we looked at the risk and I accept that risk. But people don't take it one step farther to say, well, what's the consequence if that risk actually came true? And that's where the meat of the conversation, I think, really is held. And then, we could deep dive on this for hours, but really there's a lot of ethical and legal considerations when you talk about shared decision-making between humans and AI. So in the case of, let's use something not life critical, but let's say that if Nancy Curry and the robot are out there doing something and they're working on a very expensive piece of space hardware, and the robot leads to sort of an error, or the combined human robot team, there's an error there. How do you even look at root cause and where that comes from? And how do you look at where, I don't want to say the blame, but like, where's the root cause of the error? Certainly in a car situation, if a person was driving an automated car and it hit something it should not have hit, whose responsibility is that? Was the car supposed to warn me so I could do something, or was it supposed to do something without me even having to, warn me? Or did I fail to react in time? So we're sharing that now. We're sharing, the car and I are now sharing all the decisions. So how do you decide that? I think that's a really, really rich topic area. There's probably many more.
Yeah. I do have a feeling that that we could keep you here all night discussing this. But I wanted to ask one more question, simply because of the nature and purpose of this AI Engage series, to kind of support women getting into AI and data careers. I'm going to throw one final question at you. So I know that you've done a lot of mentorship for women in STEM being at NASA. Would you share a little bit about suggestions for mentorship or career opportunities, or just even what advice you would give your younger self?
Oh, sure. So first of all, I think having a mentor is a phenomenal thing. I suggest everybody get a mentor. I think you're never too old for a mentor. So I think mentorship isn't as highly applauded as it should be. And it's very enriching for both people on either side of that relationship. And reverse mentoring, where you're being mentored by someone who is younger than you, as I think also really critical, because we're raising humans right now that are having completely different experience of technology than we did. So it's very hard for us to put ourselves in their shoes and understand what it was like to never be without a device when they were growing up. We, my Gen X, self, we were the last analog, generation. So we're the ones where the transition happened. So we have to kind of understand that. And I think we're not necessarily prepared to understand what that looks and feels like. So that kind of reverse mentoring is also really, really important. So if you are a young and up and coming person, go and mentor someone who's been at this a while and could use some insights. And then in general, I would say for advice, self-awareness is the number one. I think understanding how we function and think and emote and process is so critical, because really it's all about how we are showing up. How are you showing up for work? How are you showing up in your day? How are you showing up as a team member? I think we get very, very quick into pointing fingers at, well, it's about, we don't have the budget, we don't have the resource, we don't have the time, this person, that person's slowing me down. And it's really easy to point outward. it's much harder to look inward and say, well, how could I have shown up any differently or better for this situation? And how can I bring my best self to the table? And where could I be thinking things differently? Where could I be more open? Where could I stay curious as opposed to getting into judgment? So as we go through these kind of career development challenges, and we're learning all the time in our jobs, we hope, we're constantly, it's a cycle, we get challenges, we have triumphs, we have challenges, we have triumphs. And how we are throughout that, I think, is really, really significant. And of course, it goes with that. I don't know if it goes without saying, but it goes without saying for me, that I feel like the attention that's been given to diversity, equity, and inclusion is so, so critical. I'm thrilled that the conversation has been advanced in the last several years more than it has ever been. I think we had suffered from a very narrow definition of diversity, equity, and inclusion. And I think now that people are understanding it's about many diversity of thought, diversity of age, diversity of ideas, of backgrounds, of genders, of cultures, of ethnicities, it can be any range of things. That's what really makes a team rich. And we need that, especially as we've talked about tonight. The more opinions that we have that are varied, the more user cases that we have, the better. The more we understand who are using our products, the better that we're going to be at designing those systems.
Wonderful. Thank you so much. I really want to thank you for your time tonight. I thought this was a fantastic discussion, and I think we have some time for audience questions. So if anyone has any questions, please drop them in the chat right now. While you guys are taking a few minutes to get those in the chat, I'm going to share really quick and just give the date for our next Women in AI event, and then we'll pat back over for audience questions if that's okay.
Yeah, absolutely. And I'm also going to put in the chat too, because I do mentoring and coaching, and I have a whole business associated with that on the side of my day job. I will put my information in the chat, and if anybody wants to reach out to me, I'm happy to do that.
Wonderful. Thank you so much.
Yeah, of course.
Okay. Okay. So this is just a quick reminder. So I did mention that the Women in AI Engage series is a monthly series. So our next event is Thursday, September 28th at 5:00 p.m. So mark it on your calendars, and we'll have more information out soon. Okay, let me stop my share. Okay. Give me 1 second to compile.
No, take your time.
Thank you. Okay, direct message. Perfect. Okay.
Okay, so I'll go through some questions and then I'll type my contact. Okay, so how do you factor on human reactions when using a system? For example, driving a car. I wonder if it is safer to profile the person who drives the car and personalize the system based on the driver. Okay, so as of all answers, I'll probably say yes and no. So how you typically factor that. So my computer desktop looks different than your computer desktop. And there's a way that I like to see my information laid out, and there's a way that you like to see your information laid out. So as with any human interface design, it's at some point you have to allow individuality in how those displays and interfaces are going to look. So some reconfigurability is incredibly critical. And interestingly, we used to think about that in terms of Martian habitats when you're going to be in a space for 3 years. And if you didn't let me rearrange any furniture in my house for 3 years, I'd probably go nuts. But some other people would be like, no, don't move my stuff. So we have to think about all of that when you're talking about how people react. There is certainly a difference in how they like to see things. So it is how much do you want to have that configurable, and what are the risks and trade-offs to having that reconfigurable? So most of the time you can move things around on dashboards and screens, and that's great. But in terms of profiling people, one of the best ways to do that really is just to get a lot of data on your users. And right now, for example, in the automated car industry, when people are driving, they're taking data constantly. And so we're able to get fairly instantaneous feedback. On the defense side of the house, like I mentioned earlier, it's much harder to get. We don't get access to the soldiers who are using our equipment a lot of times. So we almost never get very direct or on-time feedback. Same thing on the space station and the space shuttle. We had many instances where post-reporting of incidences usually never work. They never rate an event as difficult or challenging after the fact as they would during it. So if you're not getting information in real time, it's usually skewed towards underreporting. So very, very important to start to profile in that way how people are using it. So absolutely. But in terms of safety, it's again, it gets back to the expense and the cost and the ability for you to actually change the way the system is functioning. Because once you change one thing, a lot of times it ripples throughout a lot of other ways that the system is operating. So you just have to kind of be careful when you're designing in that way. Pros and cons of humans viewing the AI system as a robot more like a software. I mean, we anthropomorphize everything. I mean, people form bonds with technology. People like feel like their phones are their friends. It's sort of like you almost I don't think we can help humans trying to put some sort of human framework context around an automated system or an AI system. It's sort of evolutionary. But I think I will tell you a funny story. So one of the times we gave the robot an extra joint in the neck, so it could look left and right and it could look up and down. But one time we actually put in we called it the maybe joint. And when someone's teleoperating it and you're talking to the robot and they wanted you, and like if they didn't hear you something, they would go like, the robot would go like this. And let me tell you, it's very, very provocative when your space robot is looking at you like this. So I think, and also if you look at troops who use the robot dogs on the field, they name them instantly. They are very attached. And when those robot dogs go down, they are very unhappy. Like the whole thing comes to a standstill until that robot is back up and running. So it's fascinating how that transfers. Let's see, AI is driving our behaviors. Think I would impact human behaviors and skills. Yeah, I do. I think it can. I think we can get lazy about maintaining our situation awareness. I think our sensory systems can get kind of fatigued. Remember, our brains are plastic, so we can learn, but we can also unlearn. And I want to make sure that people are thinking about what relying on a system will do to our ability to do it ourselves if we ever needed to jump in and take over someday. So for sure. Okay. And then somebody asked me, here's my contact. Somebody asked me about that and didn't have it on there. Okay. Sorry. That was the next question, but I think it was just to me. Combined pharmacy profession with AI and base bus. Okay. So interestingly, for the space pharmacy one, so we had an entire group at NASA that was dedicated to planning what a medical system would look like for long duration missions, because we can't carry everything a hospital has. So if you imagine trying to recreate an entire ER in a little tin can, it's very difficult. So we run simulations, and this is where AI came into it. We would run all sorts of neural nets and models to input all the different potential diseases, sicknesses, illnesses, bone breakage, degradations, normal age out of issues. We would model all of that into what would the treatment plan be for any of these instances that you might see on a 3-year mission. And then that would start to categorize for us. Well, if you brought an ultrasound, that would cover 35% of your scanning needs. If you brought a CAT scan, it would cover 42%, so you could sort of start to understand how critical each piece of medicine or hardware or equipment was to treating a medical event. For pharmacy, just as a side tidbit, just like food in space, anytime you put nutrients or medicine in a matrix, a food matrix or a pill matrix, it starts to degrade almost instantly. So medicine, as you know, on your shelf loses efficacy after a certain time frame. You can look on the bottle and see when you should stop taking it. And if you are trying to bring medicine that will stay fresh for 3 years and have pharmacy for that, we need to be able to predict the rates of degradation of that. We also looked at printing things in real time, like printing food and printing medicines in real time, to be able to, so you would keep it in the medical form or the nutrient form before you put it into a food matrix, so to keep it fresher, and then you would just need it in the moment. I don't know if that answered your question, but you can type another one if I didn't get to what you were driving at. Okay, unless I wrote my info, you can reach out. Yeah,
I've got another one here if you want me to throw one at you.
Sure.
What AI innovations are you excited about in the defense industry that we may see in the next 5 to 10 years?
That's Mark. He and I were colleagues, so the great question, Mark. So I would say I'm always excited about anything that creates an opportunity for our human military personnel to be as far away from danger as possible. And I think that given the amount of data that they are trying to integrate and incorporate under very stressful situations with life critical, moments, with 6 layers of chains of command, and, trying to make decisions that have to be coordinated across people and teams. I'm looking very much forward to our robotic systems and our AI systems and our DoD systems being far more coordinated into an ecosystem than they are today, so that you're getting a broader view of what's happening on the battlefield. You're getting shorter lengths of time for command decisions to be made. So there's fewer checks and balances, that they can be made more on the spot. And that we start to build these systems that are more robust, so that we can start to rely on them a little bit more than we do today, to operate in GPS denied configurations or comms dropout configurations. So it's really, to me, Mark, about stitching everything together, and allowing that communication between machine and human to be as good as it would be between human and human. We have evolved to do that very well. We are now trying to replicate that within the robotic world. And when you have so many disparate types of agents on the field, they don't all speak the same. And I think Heather asked a question about language. Language in AI is hugely important. That's where that sort of bias and culture comes in. And I've seen that time and again in the systems that we field, even just across countries, and certainly at NASA, we saw that. And like I said, many times, what one person views something as, or calls something, or labels, or what's acceptable for one, person may not be acceptable for another. So it's real, and that's all about how we train the systems. What data are you using to train it on? That's really going to influence so highly how they're utilized. So. Did I get most of the questions?
I think so. There's,
I know we're over time, so not everybody may be able to stay past the hour, but I just wanted to make sure I didn't miss a major question or.
Yeah, well, I give a round of applause to our audience. These are great questions.
These are great questions. Yeah. If somebody wants to unmute and ask something, that's fine too.
I've got one here. So as you said, AI is driving our behaviors. Do you think AI would impact human behaviors and skills? Will it make it worse?
Yeah, I touched on that a little bit, about, kind of losing our ability to maintain situation awareness. I will tell you, not to end on a grim note, but the 737 MAX, the Boeing 737 MAX crash, which I don't know how many of you are aware of that happening. That is an example of where they were trying to put AI into a system, that so that they would not have to impact the behavior of the human, and it did exactly the opposite. So the general sense of the problem is they wanted to fly, they wanted to put a bigger engine on that aircraft, and that changed enough of the control of the aircraft that rather than recertify the whole thing, by the way, I'm being grossly generalizations here, I'm being very high level, so like you can go dive into all of this, but the main crux of the problem was to not have to recert, retrain, everything. The solution was to put some AI into the system that would automatically adjust the control systems so that the flying experience was more like the crew was used to with the smaller engine. And so in the beginning, I think the impetus was, let's just not bother having to do all that, and let's not having them bother to retrain and relearn. Why don't we just make it fly like it would if this engine wasn't even on there? So, in doing that, when the aircraft didn't behave as expected, the crew had no knowledge of what was happening and didn't know how to respond, and didn't know how to correct, and didn't know what inputs to put in, had no situation awareness of what the automation was doing. And even like I said, when we put those cars out on the road without training, the first few times you try to use that system and it does something for you, you're going to be like, whoa, what was that? I don't know what's happening. And it's very scary. So, so in that case, it led to a catastrophic incident. But when we think we're building AI and autonomy to help humans, we have to be, I guess if this is the takeaway, right? We have to be careful, like I said, that we think of humans as part of the system. In that case, they thought of the aircraft as the system, and we're just going to give it to the human to run and it will be fine. But they didn't design the human's cognition and thought process, and understanding of the aircraft into the system, so that they didn't anticipate that they would ever have to interface with the autonomy, and it wouldn't be an issue. And so when we don't consider the humans from the beginning, that's when we're not doing our job. So that's why we're here and we're critical.
Yeah. These are wonderful examples. Well, we are over time. Dr. Rochlis, I want to thank you so much again for
Sure.
joining us. This was a wonderful event. So yeah, thank you. And yeah.
If anybody wants to unmute or anything else, I'll stay on for a few minutes. If people want to jump off, go ahead and jump off. Any last minute things. Thank you so much for inviting me. It was a pleasure to share with you. I hope everybody enjoyed it and learned something, and has a great week.
It was wonderful. Thank you.
Thank you.
That was terrific. Thank you so much.
You're so welcome.
Thank you very much. Appreciated it.
You're very welcome.
Bye.
Okay.
Thank you everybody for the event. It was very insightful though, all the learnings.
Thank you so much. Thank you for attending.
Yeah.
Bye.
All right.
So, Jennifer,
Mhm.
I think like I got two questions from two different people. They're asking where they can find mentor. Like maybe if you have something, because we would release the recording, if you can just briefly say it now and then they will hear it later.
Yeah, I think that's probably a question that's best asked one-on-one, because I'm not sure their situation and where they have the ability to go and find mentors. I need to know a little bit more about their specific situation to kind of guide and direct them a little bit better. So you can give them my email address, which I put on there, which is info@jenrochlis.com, and they can email me and I will get on the phone or email with them and help them find some mentors.
Perfect. Thanks.
Yeah.
Absolutely.
Thank you so much. I mean, this truly
You're so
was
welcome.
truly fascinating. These were
Oh,
great
thanks.
examples.
I'm
Love
glad.
So insightful. I learned so much. Thank you.
Oh, thank you. I'm so glad you did. Thanks for coming. And thanks for participating. It's exciting stuff to share, in my opinion. So
Well, any other last call for questions?
okay.
Okay.
All right. Well, thank you guys. Thank you for the invitation. Thanks for having me. Thanks for working with me. I'm thrilled that there's an organization like this. So let me know how I can help be a champion.
Wonderful. Thanks.
You're so welcome.
All right.
Okay. Shall we sign off?
Yes. Everyone have a
Right.
good night. We'll
Have a
see
good night,
you
everyone.
September 28th.
Have a good night. Thank you. Take care.